So we can start this last part of the afternoon. So I will give I wouldn't call it a lecture, but just a few points on a topic that is basically the same topic that Roberto presented just before, but of course sensibility are different, and also the approach is also different. So I think it is interesting just to see more or less the same topic from different point of view. And why I'm talking about forecast beyond the week. So forecast at weekly scale, from weekly to monthly scale, because at the Regional Weather Service we issue since a few years already a public bulletin on our website where we describe the weather in what we call week 2, and then we give an outlook also for week 3 and 4 together. And then also Valentina is taking charge of the seasonal forecast on the same page. So we have a web page dedicated to long-range forecast, in addition to, of course, short-range and medium-range. So I am the one in charge at the Regional Weather Service of issuing this forecast, the monthly forecast, and we do it twice per week using the ECMWF fields. But so I will describe in this presentation this procedure, and I will put also some ideas and some, yes, also philosophical ideas in the sense. So first of all, I wanted to quote this sentence that Anders said the other day, but basically I read this sentence on a paper that he wrote for I don't remember which, I think it was for a Spanish yes, magazine or El Tempo. And I think it's very important. I mean, I have rephrased it a little bit, but the meaning is this one, that the science, there are different branches of science, exploring the cosmos, the macro and the micro, so different physical forces, evolution of life, and meteorology as an important role in science. Perhaps we don't know. We think it's something a little bit marginal, but I think if I think about it, I think it's a huge also role. That is to explore the limits of how can we able to predict the future, and not. If you think about other sciences, there is not many sciences that are making prediction of the future, and this the prediction is not regarding a simple problem of few corps like planets, or it's a very complex problem and numerous problem. So you have many molecules, many interaction with many things all together, and it's amazing how we can make prediction even at 1 day, I would say. And we do it now at 10 days, and this is simply surprising. So why we can, so Roberto, I don't know, okay, Roberto is not here. Okay. Roberto just talked about this predictability and why we can predict things. And just, so a small sketch here. So the thin line between predictability and unpredictability. Why sometimes the atmosphere is more predictable and why some other time is less. And simple, in a very simple way. I mean, predictability, I'm not saying that, but others, I mean, scientists are saying This is mostly linked to inertia of phenomena and periodicity. If a phenomena is periodic, then we can predict it, and also inertia. So if something is in motion, tend to stay, persist in this state if there are no forces perturbing this. And there are intermittent large-scale phenomena like the one listed there, so Rossby wave packet, we will see that, stratospheric oscillation, El Nino, MGO, SST, and soil anomalies that may force the atmosphere towards a certain state. And these phenomena are either periodical or they have a large inertia, like the surface anomalies. Unpredictability is instead associated with rapid non-linear growth of errors from the small scale. So sometimes you have a rapid growth of error from small scale up to large scale. For example, is a typical case is a convective case when you have convection that is basically pumping up at larger scale motions that are more at smaller scale. So there is in this condition there is a very rapid upscale of energy and errors, energy from the small scales and also errors into the large scale. So in these two, this just to simply schematize two totally different type of situation in which you can have different predictability. I have also, for the joy of Anders, I have also my slide with Lorenz. Okay, this is Lorenz 2006, so it's more a recent one. And it was a sort of review paper, I think, that was in the book of the Tim Palmer and Renate. I like this. We were talking about with Anders before, with this definition of predictability or intrinsic predictability, that is the extent to which prediction is possible using an optimal procedure. And this, well, we don't know if it is existing at all or not, or just as a metaphysical definition that in any case nobody will measure it at the moment. Yeah. And then there is the practical predictability, that is the predictability that we achieve with the actual models and systems that we use to predict. But it is important to me, I mean, in my presentation also, to keep separate the two, to show that, of course, there is space, there is room to improve, even in the future. Because if the limit will be low, of course, then all our efforts will be useless. No, I don't think there is a clear limit, as we will show, but yeah, just to highlight that there is this potential difference. This is also another nice picture illustrating this concept. And this, I took it from this scientist, from an American scientist. And so we are very good in predicting things that are at let's say small to medium scale, spatial scale at small time scales. And if we go, the more we go on this side of the graph and we try to go to longer scale, then the predictability of course gets smaller. So these lines are the current predictive skill, and we want to push this line towards this region of the graph. And then this is the barrier that we don't know exactly where it is. But this also illustrates the fact that, okay, there must be a limit, because if there is no limit, it means that you can predict everything in the future, and this is, it seems quite unlikely, I would say. So if you work, you see, perhaps you cannot read the items here, but it says that if you're working on different aspects of models, you can improve predictability at the different ranges. But why all this discussion? I mean, why is it just academic, or is there any real implication in this discussion? And I think I imagine this dialogue from three meteorologists, and especially the first one is looking at the mobile phone, at the application where it is providing forecast every 6 hours for 15 days of rain with 3 decimals, as Anders was saying. So he said, look at this ridiculous website. It's providing forecast up to 15 days at 6 hours intervals of rain and so on. And we know that this is a bit stupid. So the second one, yes, says, yes, that's rubbish. Forecast of temperature and rain are accurate up to 3 days at most. So also this answer, I don't like it. And I like more the third one that says we can't establish a predictability limit a priori. This is changing with atmospheric circulation and spatial temporal scales involved. So in certain situation, a 1 day forecast for a convective afternoon, for example, might be as wrong as a 7 days forecast in anticyclonic condition. So this is to illustrate that we have to have clear this concept of predictability also to be more efficient in communicating to people. Because if we say, forecasts are accurate only up to 3 days, I think this is as bad as this one. Because that means that, we should stop at 3 days and that's it. But it is not like this. Because atmosphere is not like this. Sometimes you can go further, some other times not. But we should be able to understand why and when we can do that. So Roberto presented a nice study showing that basically showing the forecast horizon for different variables and for different time averaging. So it was a sort of demonstration with numbers of things that were clear from in the mind of forecaster from a long time. And the concept that according to the different type of phenomena that you want to predict, you have a very different forecast skill at different time scales. Was a notion that also was in the past. For example, of course, if you go from small scale to large scale, you can go up. You can push the limit further, and if you do time averaging, you can benefit of it. And for example, here in this table comes from a small paper that is on our magazine Ecoscienza, that unfortunately is in Italian for those, but most of you are Italian, so. And and then is about l'affidabilità delle previsioni meteo oggi, so how reliable are forecasts nowadays. And so if there is a sort of classification from types of evolution, so if you going from changing of flow changes to planetary waves, to cyclones and baroclinic evolution of cyclones, to convective systems. So you start from weeks up to days. So predictability is, it depends on what you want to forecast. And why? So sometimes you have more predictability than other days. Again, linking with the Roberto presentation, he mentioned the effect of MGO. So of the periodicity of tropical convection to respect to the skill of Europe. And there was this nice paper from Cassou that was presented also at the user seminar, showing that in certain phases of the MGO, so when convection, for example, is over the maritime continent, very often triggers a Rossby wave train, so a Rossby wave packet that starts from the Pacific and sometimes reach Europe. In this condition, scores seems to be better. And this is a sort of an investigation that we are now exploring with a technique that we developed together with Frédéric Vittart at this NWF. So as I had a small, a collaboration with this NWF in investigating the reason why the physical mechanism that links MGO with increasing better scores, so lower error over Europe. And perhaps, I mean, it's not a definitive answer, but sometimes you see this, there is a clear, according to some phases of the MGO, there are clear propagation of Rossby wave packets from the Pacific into Europe. And we see that we identified all the wave packet in the last, in the reanalysis in era interim in the last 50 years. And we found that, for example, and we found that you see the blue line, the green line is the average error of the Z500 over northern hemisphere, and the blue line is the average error when you have wave packet coming from the Pacific, from the West Pacific into Europe. And we found that in general this the error is lower, so the RMSE is lower, but also the anomaly correlation. In a small measure with respect to the RMSE, but also showing also in the anomaly correlation. And the red curve is also showing is a more general criteria, showing cases with Rossby wave packet not coming from the West Pacific, but in general, when you have longer wave packets, longer than 7 days, is also showing a lower error. So this is just an example. I don't want now. I'm not going into the details of this. It's just to show examples of phenomena that can improve predictability. And this, and this, the same is showing even more the ensemble mean. So the ensemble mean is showing even more this difference, and the spread as well. So the spread of the ensemble is lower when you have this propagation. And the bars are the confidence interval, and sometimes you cannot see from there, but in some in the medium range, for example, they tend to be separated. So that means that the results is significant in statistical term. Doesn't mean, I mean, it has, so it's a sort of robust evidence that, another nice example, I think this is also a nice, very nice paper from Honegger, showing that according to the type of flow over the Alps, so there is Italy here, and so you see three different types of flow, one with a sort of weak gradient, one of a short, sharp, strong southerly flow, flowing into the Alps, and another one with a southwesterly flow, not as strong as this one, but still strong. This is the ensemble mean of an EPS of limited area models showing precipitation. So there is, all these three flows are showing precipitation. And you should see this one quite a lot of precipitation, this one a little bit less. And this is the spread of the accumulated precipitation. And you have a very large spread here and not as large in these two situations. And again, they went to investigate the fact that in this type of condition, when the flow, for particular dynamical stability reason, in the first type of flow, the excitement of gravity waves and propagation of gravity waves inside convection is much larger, and this produces a very large spread in the simulation that is not present in the other two simulation. Despite the precipitation is larger in the second and in the third events. So again, this is another example of how the different condition can lead to very different spread and very different predictability. So, what about, this was just an introduction, but what about the forecast horizon beyond a week? So as I said, we do this, the monthly outlook, and so I'm going to show now how we produce this outlook, which products we are using. Well, the main source is the ECNWF, and I would say one of the main sources is the ECNWF web page. Now, this is the old web page, and I'm still using the old because the new one I got lost in the new one. I don't know if it is this. This is my feedback. You can take it home and perhaps there are more things, but I couldn't find the monthly forecast, for example. I don't know. This page is accessible to the member states, so it's not a public page. You have to access as a member state, and member states usually are the national services of the member state nation. For Italy is a special case, and we will have another week of conference about that, but maybe next time. And you have many products. You have, starting from, I start from the bottom, so you can check the tropical storm activity, if there are tropical storms in the forecast of the monthly forecast. You check, for what I said before, usually I check the phase of the MGO in the analysis and in the prediction of the monthly forecast. Then I check the mean northern hemisphere anomaly in the 4 week of forecast. So this usually, sorry, I forgot to say, all these fields, almost all these fields are coming in weekly averages. So you will have a weekly average of ensemble mean anomaly, ensemble mean of Z500, of 2 meter temperature, precipitation. You will have also cluster, and you will have also members. Okay, so So this is quite useful. Is the Northern Hemisphere 500 anomaly. You have a sort of Hofmöller diagram of the ensemble mean anomaly. Very useful as well. Clusters, members, plumes, and then probability and ensemble mean anomaly for surface parameter. So this is sort of a standard packet that ECNWS provides. Then we have some specific products that we developed here. And this more or less this is the sort of old products, but I'm still using it. So again, is a weekly average of the ensemble mean. This is the full field of the ensemble mean for what we call week 1 of forecast, week 2, week 3, and week 4. And then we have Z500 and the temperature at 850. But as you see from week 1, in week 1, perhaps sometimes, most of the time you see some sharp features like, a wave. Like also in this case, you can see also in week 2, you can see quite sharp, large wave over Italy and Eastern Europe. But as you go to week 3 and week 4, usually you see climatology, or you see very little on these maps. So it's also better to look at the anomalies respect to the climate. So you compare the weekly average of the ensemble mean with the weekly average of the ensemble mean of the climate of the model. That is run, as Roberto said, the climate of the model is run every week for the same period for the past 20 years with 5 members. So, okay. And on these maps, you see the anomaly of Z500, that is the solid lines, and the anomaly of temperature at 850, that are the shaded contour. Usually, as you go from week 1 to week 4, the amplitude of the anomaly decreases.
I have a problem here. Upper left map, you have a flow pattern over northern Germany or the Baltic Sea. Is that anticyclonic?
This is an anticyclonic anomaly.
Yes, but the lines, because you have colors, they are anomalies.
No. They are both anomalies, but of 2 separate fields. Z500 are the anomalies of the solid lines. Solid lines are Z500 anomalies. Dashed shaded contours are temperature at 850 anomalies.
So they are both anomalies.
Yes.
Okay.
Yeah. And then I also compute the mean temperature over Emilia-Romagna, the mean 2-meter temperature over Emilia-Romagna, that is this number, and the mean anomaly over Emilia-Romagna, that is this number. So in one map you have...
But still I have problem because the other 3 maps,
yes?
the solid lines look very much like the flow pattern itself.
Yes.
But they are not anomalies. They
are anomalies. They are all anomalies.
But they look very much like normal flow patterns.
Yeah, perhaps because you have a wave, and then the climate is just a zonal flow, so you have a wave, you subtract. Unfortunately, I don't have the full map of this, but... But anyway, Anders,
it looks very strange, but the other one looks quite normal, so there's...
But we will have, in the next one, we will have a case studies on and discussing, so I'll just illustrate this. And then mean sea level pressure, full field, and total precipitation in 1 week, okay? So this is the, so I was showing the upper fields and the surface field, and mean sea level pressure anomaly and total precipitation anomaly. Again, mean sea level pressure is solid contours, and shaded contours are precipitation anomaly. But this is just to illustrate, we are not going to discuss this, the case now. So this is what we had up to the, basically, 1 year, this year. Then, using these maps, using the maps on ECNWF, we produce a textual bulletin that we put on the web. Since this bulletin is quite, people read it, we were thinking to put also some graphics attached to the bulletin. So, and I think it will be useful, it will be nice to show some evolution of some variables at this scale, at the monthly scale, or at least at weekly scale. But the problem is the same problem as the trend meteorologist. What do you show? If you show every day the temperature and the precipitation, people will say, okay, but why are you showing this that after a week is not, lose all the skill? So we try to, I try to figure out some display that can provide useful information until to the point that we think it is useful. And then, in a way, highlight also the point in which, beyond which, information is not useful anymore. Okay, so what we have here, we have three things. Freezing level, the freezing level, 2-meter temperature, and precipitation. Let's take first this one that is simpler, perhaps. No, let's take the first one. So this is a monthly meteogram for Bologna, but we can produce for other locations, of course. And using the ensemble, what I plot here, I plot the median of the ensemble until a certain point, and I plot the spread of the, in this case, of the freezing level, 8, until I have data 15 days. I don't know why, perhaps later I will talk, I will ask Roberto. But you see, the other variables are going up to a month. So in this case, I stop only at 15 days. And you see very nicely in the freezing level height as the forecast is the spread is very narrow at the beginning, at least up to the first 5-6 days, and then the spread gets larger, and also uncertainty, of course. In the second one, temperature, we have two curves. The green one is the climate. So is the median of the climate from era interim for Bologna. And then you have the climate range that is, I don't remember, I think is 1 or 2 standard deviation. And then you have the 2-meter, the median of the, no, sorry, the mean temperature and the spread of the forecast. That is this cream area. The same for the accumulated precipitation from the beginning of the run. See, here is not raining, and then it starts to rain, and then the dashed line is the climatological accumulated rainfall from observation. Okay, so we could, in principle, we could put this on the web as it is. But the question is, do we want to provide 32 days daily forecast out? So there was some discussion and so on. So looking at this, for example, if we look at the 2 meter temperature, we see that the spread is increasing with days, as long the forecast days are running, up to a point that basically is not growing anymore. So it sort of saturates. So you see the cream area is stay basically the same. And at the same time, the mean temperature is approaching the climate. So the idea was to find a way to define the point where the spread is not growing anymore, and then there is a tendency to go towards climate. But it's still an attempt. I mean, we couldn't, it's not on the web yet. I still have to, I'm still working on it. But the idea is to just pick the point. In this case, it's not totally exact. I mean, I will have put it more here. To pick the point where the spread is not growing anymore, that means that you perhaps is very likely that you the forecast is going towards the mean for statistical reason, I would say. There is no signal anymore, and I think if we manage to go out with a sort of to add to this graph what we call predictability limit, or we can find a different name as well, where we shade all the rest. I think this will be an interesting way to convey the information that is never present in the forecast. That, okay, I'll give you the forecast if you want, but be aware that after this point, the information that brings is very small. Because one thing that I think is missing in our communication is this, to communicate at the level of uncertainty. And sometimes, even if you communicate probability, it's not explicit. I don't know if I am clear enough, but okay. Okay, so this is the text that we put on the web. Perhaps this is the old web page. Now we revised a little bit. But so twice per week we put on the web a description for week 2. So we have on the web we have the current today forecast, tomorrow, the next day, the next 5 days, and then the next 15 days. This one, and then the outlook for the next 50. So we cover a month, and then there is also a part for the seasonal forecast. In this case, this refers to the big snowfall we had in this particular bulletin refers to the big snowfall we had in February 2012. When we exceed basically almost a historical record of snowfall. You should have come that period, Anders. Was much higher than now. Yes, so in this period, of course, okay. In the period of February 2012, we got a peak of access, of course, at our website, and there was also a peak of access to the monthly outlook that it went up to 6,000 views per day. That is that was like 4%. The average is around 3% of the total visualization in the ARPA website, and on those days, of course, it went even up. So, I mean, people is looking at it. It's not a sort of page that is not seen. I go towards a conclusion with some words on verification. I'm not verifying the text because it's not so easy to verify the text. I think the text is the most valuable thing at the moment because, as I said, the text is a sort of I didn't say that, but what is the content of the text? I will not. Usually, what I am describing is if there is any changes, any significant changes in the circulation for the next weeks, and if there is a change in the mean anomaly of temperature, or if we can describe some possible scenarios in the future weeks. So I'm not saying in 3 weeks it will rain the 29th of May and blah, blah, blah. What I verify is the temperature and precipitation anomaly over average over the Emilia-Romagna. So I take 9 grid points more or less centered over Emilia-Romagna region. Emilia-Romagna region is this one. And I verified this spatial average with the observation, average of the observation over Emilia-Romagna for temperature. For precipitation, it's slightly different. I use a smaller region because we had a sort of a specific application for a smaller region. So there are two different ways of verifying it. But as you will guess, temperature is more skillful than precipitation, but I will show you. Now we are looking only at Monday. You know, the ECNWF is running monthly at twice per week, Thursday and Monday. Monday has the advantage that the first week are the first 7 days of forecast. And so you are using all the forecast. You are not throwing away the first 4 days as we does using the Thursday. So the Thursday forecast is less skillful than the Monday forecast. So we start with the Monday forecast, and in this case, I simply show from 2012 up to 2015. So almost 3 years. The weekly anomaly observed weekly anomaly of 2-meter temperature in Emilia-Romagna, and are these blue bars. You see the most striking thing is that most of the time are positive. You have very few negative temperature anomalies. The most relevant is the anomaly of February 2012. That it went up to -6 degrees of week anomaly in the week. So it was a very cold week. For 2 weeks, we had very cold weather. And the two lines are the anomaly in the forecast, in week 2 forecast and in week 3 forecast. So is the ability of the model to predict this anomaly. And you see for the big snowfall and for the cold spell of February 2002, at week 2 there was a very good prediction. And also week 3 was not bad, although the amplitude, of course, was not as large as the observed. You may say, okay, but because the forecast is always, once it is in a certain state, it will stay in the same state. So, but this is a very good case because just before and after this cold spell, it was very warm. And the monthly forecast was able to see this change. So this is really interesting, and I also wrote a paper for the ECNWF newsletter about this case.
But
and
the climate, is that model climate or observed climate?
Observed climate.
From which period?
Now, the observations are compared with observation climate.
And the period?
the period is, I think this one must be the 72,000. It's not the two climates in this. No, sorry, no, I recompute this, and now these two periods are almost overlapping. So I take from 1990 to 2015. So to mimic the climate of the ensemble. And so, okay, 2012 was okay. But also it is interesting to see this long spell of warmth, and usually the model is able to see this long spell of anomaly. Then is not able really to see very well this, let's call it high frequency, but it's not high frequency because we are talking at week, these are weekly averages, so every bar is a week. But I would say when you see this, for example, let's take this summer. This summer is this one, where we had cold. But you see some week were cold, some other week were warm, so this type of variability was not seen. But the long spell are seen quite well. And in fact, if you compute, so what I did is to compute few let's say deterministic scores. So I computed the correlation between the two anomalies, the observed anomaly and the forecast anomaly at week 1, week 2, week 3, and week 4. So as you would guess, week 1 is the best, is basically are the first 7 days. So if you compute the anomaly correlation, you end up to 0.96. That means that is not perfect, but it's very close to reality. Okay, week 1. If you go to week 2, it drops to 0.77. If you go to week 3, 0.46, and week 4, 0.29. But as Anders explained, I mean, before judging these numbers, you have to look at other things to try to understand if this is okay, we are talking about, again, time averaging ensemble mean anomalies. So, okay. So what for example, I have computed also other metrics, and you see the mean absolute error is increasing with the weeks. The bias is pretty large and negative. And also the variability, the standard deviation, the activity of the ability to see changes is also interesting. And especially this, I would say. I mean, if you compute the correlation between week 1 anomaly, week 2, and week 3 and week 4 in the observation, you get the gray line. So that means that after there is a correlation between the observation that is decreasing, is basically disappearing after 2 weeks of so usually it means that in the observation, when you have a large anomaly, it stays up to 2 weeks. Then from the 3rd week, it starts to decrease. Okay, so there is a correlation. That means that it gives you an idea of the persistence of the anomaly on average over the Emilia-Romagna. If you do the same with the forecast, that is the blue line, then you find a sort of higher autocorrelation in the forecast. So it means that the forecast is too much persistent respect to observation. And then you see that also in the standard deviation here. That means that basically only week 1 has the same degree of variability of observation. All the other weeks in the forecast are, the variability is lower. So the system is not able to show the degree of variability that is observed in nature, and it decreases as with time. But anyhow, I mean, I think this is an interesting result, and is based on 158 forecasts, so it's not a small number. Okay, now, so if you take, these are the Monday runs, as I said. If you take the Thursday runs, it goes down quite sharply, because you throw away the first 4 days of forecast, and so you shift all the weeks in far away into the forecast steps. For precipitation, as expected, the skill is lower, but in the first two weeks, so week 1, okay, is expected. Week 2 also has some skill that seems to be higher than climatology. This climatology is slightly different from temperature because, as I said, are 2 different data sets. So this one is not is a wider climatology from 51 to 2011. So, and then week 3 and week 4 basically there is no apparent skill. And for Monday runs instead, it is improving a bit. So that was more or less all I wanted to say for today. And the next, in the next lecture, I will present a case study, 1 or 2 case studies of the monthly scale. One will be the one about the snowfall, the cold spell of 2012. And we'll see if I will be able to produce also something about the recent cold spell that was also seen by the monthly forecast. But I like to close with this, to quote Italo Calvino, that is an Italian writer and very influent in the intellectual environment. And I found, I mean, rereading this book, Le Città Invisibili, that was written, I think, in the 70s or perhaps end of the 60s, there was this sentence that was really quite impressive, because it's so close to what we, to our approach that basically, yes. So it says, I say in English because I mean, you can read it in Italian, but the future that are not became true, so they are just dead branches of the past. So it seems to put forward the idea that for each time, at each time there is a possible, there are possible futures or possible scenarios, but only one will be truth. And the same, I think, is with forecast. At each time we know that there is not only one, there is no a single solution. There are many solutions according to how far we want to go, we want to forecast. But to understand which one will be the truth is, I don't think, I don't know, it is possible. But at least we should understand which is the range of possible